Thank you for the introduction, and a huge thanks to Piero for putting this festival together. Oh, there seems to be a microphone. That would be great. Okay.
Testing. Okay, can you hear me? Yeah. Great. Well, a huge thanks again to Piero for organizing what I believe is the third last festival. It's really an honor to be here. As was mentioned, my name is Dionne. I'm an assistant professor of material science and engineering here at Stanford University. And broadly speaking, my group is interested in nanomaterials and using nanomaterials both for energy-relevant applications and for bio applications. I'd like to give you a little bit of a flavor of what my group is doing and kind of a bigger picture of where nanoscience is headed. In particular, how we can use nanoscale engineering and the ability to image at the nanoscale and manipulate at the nanoscale to have both a cleaner planet and a healthier population. First of all, a little bit about the title slide. On the right-hand side, or I guess your left-hand side, is a satellite image of the Indus River Delta. The Indus River is, of course, one of the longest rivers in Asia. And on the right-hand side is a material made in my lab. For a sense of scale, on the left you're looking at something that's about 16,000 square miles. On the right, it's about 1 square millimeter. And on the left, of course, you know that the color comes from just the landscape, like the vegetation or whether there's water. On the right, the color that you're seeing emerges from how the material is structured at the nanoscale. So with dimensions on the order of just a few nanometers. This morning or this afternoon, you've heard some pretty mind-blowing talks about artificial intelligence, space exploration. I just wanted to make sure we all have a sense of scale for what I mean when I say nanoscale. So if you don't already feel a little bit kind of small in the universe, let's step back and take a look at the size scale of the visible universe. Unfortunately, part of the title's cut off, but at least you can see that the size of the visible universe, or the observable universe, is 9.3 times 10 to the 26 meters. So the numbers are up here. They're basically 26 zeros. It's enormous. Zooming in to just one of these dots. One of these dots corresponds to clusters of galaxies. And the size scale, say, of the Virgo supercluster, a mass concentration of galaxies, is about 10 to the 23 meters. Zooming into one of these small dots, we see the Milky Way galaxy, which is 10 to the 21 meters across. And of course, we're just one small component of that Milky Way galaxy in the solar system. The distance approximately from the Sun to Pluto is 10 to the 12 meters. And then zooming in, of course, we have the Earth. The diameter of the Earth is 10 to the 7 meters, so about 10 million meters. Looking at Everest, the height of Everest is about 1,000 meters. The length of Stanford's linear accelerator, which is just up Sand Hill, I recommend you visit there if you have the opportunity before leaving this festival, is about 1,000 meters. The height of a redwood tree is 100 meters. The size of an ant is just about 4 millimeters. Zooming in 2 orders of magnitude more, the size of pollen is 50 microns. So a micron is a billionth of a meter, or rather a millionth rather. And then we heard a lot about biology. The size of a red blood cell is 7 micrometers, so smaller than the width of a human hair by about a factor of 10 to 100. The typical size of a virus is on the order of 100 nanometers. And then we'll be talking about materials that have sizes on the order of a virus, or even smaller. So here's a scanning electron micrograph image of a nanoparticle, where each dot you're seeing corresponds to an atom, basically a column of atoms because it's a spherical nanoparticle. Since it was imaged in a scanning electron microscope, you obviously can't see any colors, but the size here of this nanoparticle is 2 nanometers across. So each atom you can see is just fractions of nanometers. So the first message that I want to share with you is why nanomaterials are interesting to look at. Basically, the entire universe is composed of nanomaterials, atoms arranged in periodic or aperiodic arrays. Generally, we're used to thinking about bulk materials, but nanomaterials do exist in nature. We can also engineer them in the lab to have very unusual properties. And I want to give you a flavor for what some of those unusual properties are. First, let's consider bulk silver. We know that silver is a good conductor, it's also shiny, it's reflective. If we nanostructure it such that we have nanoparticles that have dimensions on the order of 10 nanometers to 100 nanometers, and we look at their color, it turns out that these nanoparticles can scatter very vivid colors, ranging from blues for the smaller particles to reds and oranges for the larger nanoparticles. So simply by taking silver and making it smaller, shrinking it down to length scales on the order of just a few tens of nanometers, we get very different scattering. This is something that we can now control well in the lab, but if you walk over to the Stanford Chapel, or if you go to certain museums, you may find, for example, stained glass windows, or here's one of my favorite examples, the Lycurgus cup. It was a vase made by Roman artisans in the 4th century AD. And if you look at the cup in reflection, so if the light source is outside of the cup, you take a picture of it, you'll notice it looks this really beautiful jade green color. Whereas if you put your light source, like a light bulb, in the center of the vase, you'll notice that it looks this really brilliant red color. So simply by visualizing the vase, either in reflection here, or in transmission with light coming through this dichroic glass, you notice very different optical properties. And the two colors you see here are actually made by nanoparticle impurities, metal nanoparticle impurities that the Roman artisans would introduce into their glass-making process to give rise to very vivid optical colors. And that's the same sort of response that you'll see over in the rose windows of the Stanford Chapel. The colors that you see coming from stained glass windows come from small metallic nanoparticles in the glass that are giving rise to very different scattering properties. Like I said, in the 4th century AD, they couldn't necessarily control the process, but it's one that we can now control with a very precise level, almost atomic scale precision, and one that my student has used to make his own version of kind of micron scale rose windows. Here's an atomic force microscope image of various nanoparticles arranged to look like a rose window, and then when you take an image of it in an optical microscope, it looks just like stained glass windows. So the optical properties of metallic nanoparticles are quite a bit different when compared to bulk. I also want to give you an example of semiconducting material. Semiconductors are, of course, the heart of all of the technologies like cell phones and laptops that we appreciate today. Instead of focusing on silicon, kind of the main semiconductor that's in all of our devices, I want to focus instead on a more visually appealing semiconductor, cadmium sulfide. If you go to Michael's, the art store, you wind up buying cadmium yellow pigment. It's basically a powder of cadmium sulfide crystals immersed in an oil medium. And you'll notice that it looks kind of yellow. It's in fact the same pigment that Van Gogh used in his painting, Café Terrace at Night. So here the powders are composed of micron scale crystals of cadmium sulfide. But if we nanostructure it such that we have a 2 to 5 nanometer nanoparticle, which we can make in our lab, you'll notice that, again, the color can look yellow, but under ultraviolet illumination, it can fluoresce a very vivid green color. And we can tune the fluorescence of these particles simply by tuning their size. So smaller nanoparticles tend to fluoresce in the blue, whereas larger nanoparticles tend to fluoresce in the red. And that change in fluorescent color comes from quantum confinement. So now we're patterning materials on such a small length scale that quantum effects are starting to significantly impact the optical properties. So you may wonder, if we have the ability to make nanomaterials, and they do have these different properties, what can we use them for? Maybe the simplest example to point out is that nanomaterials allow us to make smaller devices, as you may expect. So here's an image of the iPhone 5. It weighs about 0.3 pounds, costs roughly about $200 today. And while we may not be so pleased with the battery lifetime, it's rated at 300 hours for standby, and it takes generally about 2 hours to recharge your iPhone. Now going back to 1984, some of you may remember Gordon Gekko, the Wolf of Wall Street, and he used his phone, the Brick, It's called the Dionne phone, manufactured by Motorola. It weighs about the weight of 10 iPhones, so it's quite a bit heavier. Probably wasn't as convenient to carry around. It also could only store about 30 phone numbers. Now, does anyone remember how much the Dionne cost? Okay, well good. Probably none of us were wealthy enough to afford one back in 1984. But back then, it cost close to $4,000, which in 2015 dollars is about $10,000. So enormous cost. And the battery lifetime was only an hour on standby. That means you could basically make one quick phone call if you wanted to, say, facilitate a trade on the stock market. And then it took 10 hours to recharge the phone. So not only have nanomaterials allowed for smaller devices by virtue of, say, how many transistors we can fit on a chip, but part of the advances in going from 1984 to here is because of advances in batteries. And that's an example I want to give you from my own lab. So if we take a scanning electron micrograph of a battery electrode, it looks like this. Here's a scale bar. The white bar is 1 micron across. And you'll notice that there are a bunch of nanoparticles. Here they're kind of falsely colored to indicate different types of nanoparticles. But all of these nanoparticles are a material called iron phosphate. And when you're charging up a lithium-ion battery, basically lithium ions are going into those nanoparticles, those iron phosphate nanoparticles, and creating lithium iron phosphate. And when you're charging and discharging a battery, your goal basically is to get as much lithium into that nanoparticle as quickly as possible. That way you can charge things up quickly, and then you have very high capacity, because the lithium is what's giving you your energy out. And it's been shown kind of in empirical ensemble studies of nanoparticles that when you nanostructure materials, especially for batteries, first of all, you're going to have faster kinetics. If the goal is to get lithium in as quickly as possible, you can imagine that by having a higher surface area to volume ratio, it's going to be much easier for the lithium to diffuse in or to interpolate into the bulk of that nanoparticle. So generally, you can charge your battery much more quickly and get lithium in there. Secondly, these nanostructured batteries that you all carry around in your pocket have an extended life cycle, meaning you can charge and discharge them many, many more cycles than you used to be able to do with a Dionne phone back in the 1980s. And that's because these nanomaterials are less prone to defects. So unlike a bulk material, if you were to introduce a defect by charging it up with lithium, then that whole material would basically be broken. Now when you have nanoparticles, if there are defects introduced in just a few nanoparticles, it doesn't matter because most of the other nanoparticles are quite robust to defect formation and can maintain their storage abilities. And then finally, another interesting point is that there are size-dependent and size-tunable thermodynamics. So compared to bulk materials, it's actually much easier to load up these nanoparticles with lithium. So you need a lower lithium concentration to have all of the lithium basically be absorbed into the nanoparticle and be able to get as much juice out of your battery. So nanoparticles offer a distinct advantage, but if we want to engineer better batteries, then what we really need to be able to do is somehow visualize how ions are intercalating into different nanoparticles. And you'll notice in this scanning electron microscope image that there are nanoparticles that are much smaller than a micron, but the problem is right now, or until recently, there haven't been any techniques to kind of directly visualize how each of these nanoparticles is transforming to allow us to make better battery materials and to be able to identify which nanoparticles are best at giving you the fastest kinetics, the longest cycling, and the highest energy capacity. But my group recently has worked on a technique that allows us to directly visualize the ion intercalation and basically the phase transformation that's associated with ions going in and out. So how can we engineer better batteries from the bottom up? The key is coming up with a visualization technique that allows you to observe it. And just to illustrate it, I want to show you a movie where we're going to be looking at ion intercalation into a square metallic nanoparticle. Here the scale bar is just 10 nanometers across. So this nanoparticle is just about 40 or 50 nanometers across. And again, each little dot you see here corresponds to an atom. So here we have a single crystalline metallic nanoparticle. Ions are going to flow into it. And then if we look at a video of how ions are intercalating in, if we kind of fix our ion concentration At this particular concentration, in this particular time, the ions have completely filled up the top part of the nanoparticle, the bottom part of the nanoparticle, and they've actually entered in through a channel of the nanoparticle. So the white part corresponds to where this particle has already been charged up. The dark part corresponds to where it hasn't been charged. So it's kind of neat that here you're visualizing with roughly about 2 nanometer resolution how these battery materials are charging up. And now as I hit the play button, what you'll be able to see is that as a function of time, sorry it's a little bit shaky, we haven't done the motion correction yet, but you can see the white phase front is going to be moving in from the left. So lithium is now intercalating in over here. It forms kind of a little bit of a triangular phase front. This is also taken in real time. And then after about 15 seconds, this particle becomes completely white. So it's completely charged up with ions. So now what we can do is look at individual nanoparticles and figure out which materials load up the fastest and how can we get the most energy storage, so get the most lithium charged in there. I also have just a series of snapshots that kind of visualize that phase transition. Again, the scale bar here is 40 nanometers. Okay, so that's a little bit of a flavor for how nanoengineering is allowing us to make better battery materials for energy storage. I want to spend a little bit of time talking about nanomaterials for medicine as well. And there are a couple areas that my group is really interested in. The first is in light-mediated and enantioselective syntheses. It's kind of a handful. If you haven't taken organic chemistry, I'll talk you through it. The idea is that there are many pharmaceutical drugs that rely on the specific handedness of the molecule and how that molecule interacts with all of the proteins and molecules in our bodies. So it's known that our sugars and our DNAs have a particular handedness, and that handedness can basically only shape with another handedness of a molecule in order for the drug to be effective. But with many pharmaceutical companies, it's actually quite expensive to kind of filter out the wrong handedness of molecule. So there are some drugs on the market, for example, Advil, where there are 2 handednesses of molecules. So you can see here's a different molecule, say the right-handed version and the left-handed version. And Advil, as a pill, comes with both handednesses of the molecule in it. And it turns out the one that's not effective for us doesn't really do much, but only 50% of the Advil that you're taking is actually effective for pain relief. There are other drugs where the wrong handedness can actually be extremely deleterious. Thalidomide being one of the more famous examples from a few decades ago, where one enantiomer, the S version of thalidomide, was known to treat morning nausea in pregnant women, whereas our thalidomide was known to induce birth defects. And they didn't realize this before they marketed the drug. So there are many examples of pharmaceutical drugs where we want to be able to easily purify the drug to be able to have just one handedness or an enantiopure synthesis. And what we're doing is instead of coming up with chemical techniques, coming up with light techniques. So if we can just take a synthesis that has both enantiomers in it, shine light on it with the appropriate nanoparticles that allow the wrong handedness to selectively absorb light, and that molecule basically gets zapped or burned off, and then we wind up with an enantiopure solution. So this is one area where light and nanoparticles are coming together to create better, more efficient drugs. A second example is in an area of in vivo force and field sensing. We're coming up with nanoparticles that give off visible light when illuminated in the near infrared, and then working with clinicians and biologists to develop nanoparticles that are sensitive to both forces and fields. So for example, you could use these nanoparticles to map out how neurons are transmitting signals when there's an electrical pulse that's traveling along the axon. Or for example, detecting any heart disease before an arrhythmia is even detected. Your doctor could just inject these biocompatible nanoparticles into you, see the visible change in color when your heart cells exert different forces on each other, and then be able to detect an early onset of heart disease. One other quick example is in molecular sensors. Some of them are so efficient as to be able to detect single molecules. There are also a handful of sensors that now can be integrated into your cell phone, so you can just simply use your cell phone camera to be able to detect the presence of certain molecules. And of course, one of the maybe more commercial One of the earliest commercial applications of nanotechnology was in home pregnancy tests. It relied on metal nanoparticles changing color when there were certain hormones that bound to the nanoparticles. The one I want to focus on in my talk, though, is a light-mediated cancer treatment. So how nanoparticles plus light can help in ablating various tumors. So the idea is that if you have a localized cancer, you can insert different metal nanoparticles into the tumor and then shine light on it. The light is going to excite the electromagnetic modes of the metallic nanoparticle and basically cause the tumor cells to pop open. Here's a quick picture that I'll show you before going into the details of a mouse before being treated with this light-based treatment and after, and you'll notice that the tumor has shrunk down. It took about 10 days of this light-based treatment with maybe an hour of illumination a day for this treatment to be successful. And I will mention that after 10 days, the mice remain cancer-free for the rest of their natural lifetime. And now this is a technology that's in the final stages of FDA approval, particularly for head and neck cancers, where it tends to be quite difficult to get chemotherapeutic drugs. So you may be wondering, why do I want to use nanotechnology? What are the advantages of nanoscience over, say, molecular engineering? And to answer that question, I want to take you back to some of the origins of chemotherapy. So first of all, many of you probably know that science is kind of a non-linear process. Oftentimes, you go to address one question, and along the way, you wind up discovering 100 more questions that you have, and you wind up taking many forks in the road that lead you along a path that was completely unexpected. So talking a little bit about the origins of chemotherapy, in 1964, scientists were interested in studying how bacteria grew under the influence of an applied electric field. So they set up an experiment where they had 2 platinum electrodes and the bacteria in between kind of swimming happily in kind of a salty solution, a salty water solution. And they found that when they applied an electric field across these 2 platinum electrodes, the bacteria continued to grow in size, but they stopped replicating. They're like, oh, this is interesting. So they tried it again with different electrode materials, say silver or copper, and they found that they couldn't reproduce the results there. So eventually they decided it must actually be due to formation of a new molecule in the solution rather than the electric field. So they traced the formation back to this molecule. I'll show you a picture of it here. It actually exists in 2 different forms. So the molecule has platinum, a central platinum atom that's surrounded by 2 chlorine groups, shown here in blue and gray, and then 2 chlorine groups, shown here in green. And there are 2 different ways that this molecule can exist. For those of you who have taken organic chemistry, you'll be familiar with the cis form of this molecule, which has the 2 ammonias kind of sitting right next to each other, the 2 chlorines right next to each other. There's also the trans form, which has the 2 ammonia groups kind of bridged by that platinum group. So inspired by the fact that they were able to stop the bacteria from replicating, Rosenberg, now known as the father of modern chemotherapy, decided to take these 2 molecules and inject them into mice that had localized tumors and see what happens. And he found that when he injected cisplatin, that cancerous cell division was completely inhibited. But when he injected the trans version, nothing really happened except the mice started to become a little bit unhealthy. So how is it that cisplatin works as a chemotherapeutic agent? And actually, if you have friends or relatives who have unfortunately had chemotherapy, this is a very common one. It has close to a 100% success rate for testicular cancer. So how does it work? Here's an image that maybe those of you in the back can't see, but you can inject cisplatin into the bloodstream. It's a small molecule, so it can either be directly injected, or you can inject it via small polymeric nanoparticles, basically kind of cell mimics, liposomes that will fuse with the cell wall and then enter the cell. So when cisplatin is in your bloodstream and enters a cell, outside of the cell, it holds on to its chlorine groups. But once it's inside the cell, there's a lower chlorine concentration. So cisplatin basically liberates those chlorines to the cell. It makes its way into the nucleus and eventually can bind with the DNA. It binds in particular with the guanine groups. So it's liberated its chlorines, which means it has two bonds. So it really wants to bond with two other entities. And it does so usually by bonding with the two carbon chains of the guanine groups in our DNA. The thing is, the guanines usually tend to be a little bit further apart than cisplatin would like. So cisplatin, the molecule, pulls on these guanine groups and kinks the DNA a little bit. So you can get kind of a two-dimensional schematic for how that kinking works. And the kink caused by chelation, chelation being a fancy term for forming a ring by virtue of there being those two bonds that form with the guanine groups, the kink renders the DNA incapable of replication or repair. So in all of your molecular machines are feeding DNA through the replication system. It comes across this kink and it's like, oh, something's wrong with this DNA. I'm going to stop replicating it. Also, there are these so-called high mobility group proteins that are kind of floating around in your cells trying to find defective DNA, and the kink makes it recognizable to these proteins that then can target the molecule for death. So this is how conventional chemotherapy works using cisplatin. You can imagine there are a couple disadvantages of it. First of all, it relies on platinum, a heavy metal, so not the most biocompatible material. Secondly, you'll notice that it's pretty non-specific. It's going to target both healthy DNA and cancerous DNA. So instead, what some of my colleagues at Rice University have worked on are making gold nanoparticles with a silica core that rely on that light-based cancer treatment. And you may say, well, why do I know nanoscience is better than this molecule? First of all, gold is extremely biocompatible, and in fact, if you've had a fancier pastry before, you've probably ingested some form of gold on gold leaf. So the way it works is that light irradiates these gold nanoparticles, which are designed to have electromagnetic resonances in the near-infrared part of the spectrum. So when near-infrared light shines on these nanoparticles, the electrons kind of slosh around the gold shell, creating intense electromagnetic fields right near the edges of the gold that kind of locally heats up the cell wall. And these nanoparticles can either passively target tumors. Tumors are known to have leaky vasculature, so the nanoparticles kind of get sucked up by the tumor. Or you can also put molecules on the surface that can bind to specific tumors. So it's known that this can be done for breast tumors and also for head and neck cancers. So once the nanoparticles are there, you just illuminate in the near-infrared where tissues are known to be transparent. If you've ever taken a flashlight and held it up to your hand, you've noticed that a lot of red light comes through. So the infrared is a window of transparency for our tissues. The electromagnetic fields induced by the electrons in the gold locally heat up the cells, causing the cell walls to pop open, and thus the cancer cells basically die. And then your renal system naturally flushes out the nanoparticles. So like I said, this is a technology that now is in the final stages of FDA approval and working in mice. It basically was 10 days of 1 hour of irradiation. So I think it's a really promising alternative to conventional chemotherapeutics. Okay, the final topic I want to talk about is a little bit more esoteric but more fun. I'm using nanomaterials to mimic masters of disguise. So here's a video of cephalopods. You guys may have seen this video before. In a few seconds, the video will play backwards. So really remarkable camouflaging. So our group is trying to make synthetic versions of cephalopods. It's not completely well understood how cephalopods camouflage themselves so well, especially since they're colorblind, so they don't even know what colors they're looking at. One way you can imagine doing it, though, is creating material that goes from being a particular color or set of colors to basically being either transparent or to allowing an object that it's sitting on to be cloaked. So how would that cloaking work? Here are some schematics showing you basically ray tracing of light. If we have just a light source with no object and we're an observer, say sitting down here, then obviously we're going to see that light source very clearly. If we insert an object in the front of the light, you'll notice that that object is going to cast a shadow. There also will be some light rays that would be scattered back. And based on how light basically propagates through the object or around the object, we wind up seeing that object, the various colors of it, or the shadows that are cast by the object. If we want to make an object invisible, then basically we want to mimic what an observer is seeing over here, or basically any part around the source. So where we just have free space when the object is there. And one way of doing that is to put a cloak around the object where the light passes through the cloak and then gets diverted around the object and emerges on the other side as if light had just passed through free space. If you look very carefully at how light needs to refract when it's going through the cloak, you'll notice that it's kind of going straight in, but then it's getting bent to pretty steep angles over here. And if you work through the math of what those angles need to be and what refractive indices are needed to create that structure, the refractive indices need to be lower than air, so less than 1, and in some cases even less than 0. So you need to be able to create a negative refractive index material. Just to give you a few photorealistic simulations of what a negative index material might look like, they don't exist in nature, but I will tell you we can make them in the lab. Here's an image you're quite familiar with, just a straw refracting in positive index water. If water were to have an index close to 0, it would look quite a bit more reflective. And if water were to have a negative refractive index, now you'll notice that the straw gets bent to the wrong side. And also you'll notice you can't see the bottom of the glass anymore. It's almost as if you're an observer looking at the glass from below, even though you're looking at it from straight on. So negative index materials give you a little bit of a kind of peek around the corner. Also, what would motion look like in a negative index world? Let's pretend we're dropping a ball into water and viewing what's happening from the top. So let me play this video. So we've got our ball right there with the shadows where it just fell into water. And even though it's getting deeper, it looks like the ball's getting closer to you. This is actually a hint that you can use negative index materials to image well below the diffraction limit of light, and then as you get past a certain depth, it looks like the ball is getting smaller. I'll play it one more time so you can get kind of a better view of it. So we drop it in. You'll notice not only does the ball get bigger, but at some critical depth where it appears to look infinitely large, these two colors switch around. So now the red is at the top. So negative index materials have really unusual optical properties, but a lot of promise not only in being able to mimic cephalopod skin, but also in creating microscope lenses that can allow us to image well below the diffraction limit of light. It turns out to be somewhat straightforward, I'd say, at this point, to be able to create negative index materials that work at microwave frequencies, so very long wavelengths. My group is really interested in creating these metamaterials at visible frequencies and in getting them to work over a broad range of optical frequencies. So here is a simulation of a crescent-shaped structure composed of a tapered metallic shell on top of a polystyrene core. And you'll notice that there are tunable indices, some of which are negative, some of which are large and positive, across hundreds of nanometers in the visible and near infrared. So we can get negative indices here over about 200 nanometers in the red portion of the spectrum, and about 120 or so nanometers in the near infrared. We've been able to create individual, I guess, meta-atoms, if you want to call them that. So here are these crescents. To be able to create a tunable refractive index, you need to put them in an array, just like you would in a normal material. In a normal material, you have atoms arranged in a periodic array. Here's a simulation, though, showing that we can indeed get negative refraction through a bulk prism composed of these little metal dielectric crescents. So we're en route to demonstrating kind of broadband negative refraction. Along the way, I just want to show you how light interacts with this nanoparticle. So these are experimental videos where we are visualizing how light is interacting with this nanocrescent. So keep in mind it's about 100 nanometers across. We've got our tapered metallic shell, our polystyrene core, and what I'm going to show you in this video is basically where light is concentrated in this nanoparticle. So we start off at a wavelength of 470 nanometers. There turns out to be quite a bit of light emission from the polystyrene core, and then some light that's being emitted from the gold shell. And as we sweep the wavelength, you'll see how light likes to concentrate itself at shorter wavelengths, at the base of the crescent, and then at longer wavelengths towards the tips of the crescent. So I think this is a really cool technique that we've termed nano-optical tomography, basically allowing us to visualize light matter interactions with about 10 nanometer voxel resolution across visible and near infrared wavelengths. So this is an individual crescent. If we make large area crescents, actually brings me back to my title slide. That orangish image I showed you was nanocrescents arranged in a periodic array and embedded in a polymer. Here's a more zoomed in image. Each of these black dots corresponds to those nanocrescents, basically the metamaterial building block that gives us the tunable index we need to make squid skin. And then based on the size of the polystyrene bead, say 165 nanometers, the thickness of the metal that we put around it, and then the material that it is either sitting on top of or embedded in, either in a polymer, PDMS, or sitting on top of silicon, you'll notice that we can create virtually any color we want. And what's cool is that we can essentially dynamically change the color that we see just with the chemical input, which is basically how a squid works. There are either chemical inputs or voltage inputs that are allowing the squid to dynamically change its color to match the background. So with that, I just want to end with a few thoughts on nanomaterials challenges for our generation and what I think the future might hold. First of all, nanomaterials are allowing us to forge new paths and new technologies in clean energy, enabling us to have solar cells that can, say, use much more of the solar spectrum than conventional solar cells, or to create solar fuels where we can basically take the intermittent energy that comes from sunlight and be able to store it and transport it in an energy-dense fuel. And then it's also allowing us to have improved battery technologies. Those are some of the videos that I showed you at the start of my talk. Then nanomaterials are enabling us to forge new paths in environmental materials engineering. I focus mostly on energy and medicine, but I think one of the most critical problems that our generation will face in the future is water, having clean water. And there are fantastic groups on campus doing really remarkable work with cleaning up wastewater and also water desalination. Of course, you can imagine incredible advances with nanotechnology in biomaterials, whether in tissue engineering or say in bone repair. Advanced computing, nanomaterials are enabling us to have new devices that can allow us to compute with light instead of with electrons on a deeply sub-wavelength level, or enabling new quantum computing schemes, or even new computing schemes that mimic how neurons are computing. And then there are going to be advances in imaging, visualization, and augmented reality. On the imaging front, there are nanomaterials that are being used for creating very efficient holograms. And then new engineered materials, kind of like the cephalopod skin I talked about before. But in addition to the optical realm, there are a lot of really cool mechanical materials that are arising that are, say, stronger and lighter. And to quote Steve Chu, he said, "What the world does in the coming decade will have enormous consequences that will last for centuries. It is imperative that we begin without further delay." I think my group and many groups across campus are trying to take that attitude to heart, and knowing that if we wish to make a new world, we do have the nanomaterial ready. So thanks very much for your attention.